Hello everybody, welcome back to another lecture for second year physical chemistry, and today we're going to discuss the chemical potential of gases. What will be covered and why? We want to apply what we know about chemical potential and do it to gases. We want to understand gases because it will enable us to understand liquids and solutions, and ultimately where and what equilibrium constants are. So this is part of a necessary process to get to the end. What you will need. Lectures. You will need to remember the Gibbs-Duhem result. And you'll need the fundamental equation of chemical thermodynamics. Mathematics. You'll need calculus. You'll need to be able to do integration, and specifically integration of the equation of the type 1 on x dx. And Atkins is physical chemistry. Please consult the second and third laws combining the first and second laws. Alright, what do we know so far? From previous lectures, we have found out that the chemical potential is the molar Gibbs free energy of a substance, or if there are multiple chemicals in a system, then it is the partial molar Gibbs free energy. And that the chemical potential indicates the inherent available or potential chemical energy of the substance. So in direct analogy, just to help you further internalize what the chemical potential is, consider the following two equations. On the left, we have dE, that is the infinitesimal change in energy, is equal to voltage times the change in charge. The change in the energy of a system due to moving of an electrical charge is related to the voltage, or as known as the electrical potential. So now compare that to the left-hand side equation. The change in the energy of a system due to change in the amount of material is related to the chemical potential. So that is something to mull over. Alright, the chemical potential derivation. Now the chemical potential of liquids and solids do not change very much due to incompressibility. However, not true for gases. We are going to consider the following. Say a gas, say nitrogen, in a cylinder at room temperature. What is the chemical potential? Well, there's your, on the right hand side, there's a cylinder of compressed gas with nitrogen in it, and we are going to make it a very simple conceptual thing by talking about a box with stuff doing nothing. So that's how we're trying to take something in the real world and trying to make it easy for us to conceptualize and then to apply thermodynamics. All right, let's get to it. We know that here is the fundamental equation of chemical thermodynamics. And what we're going to say, there's only one kind of gas, right? It's nitrogen. Thus, I is equal to 1, and our equation just becomes this. Alright, we are not going to change the amount of gas in the cylinder. It is just sitting there in a lab somewhere. Or if you're into the nitrogen ice cream making things, it's sitting there in some ice cream parlor doing nothing. Thus, the change in the particle number, or the change in number of moles, is equal to 0. So the sum is getting smaller. We're at room temperature. So the change in the temperature is 0, and we're left with this equation that the change in the Gibbs free energy is equal to the volume times the change in the pressure. Nitrogen is close to an ideal gas, so we are going to assume PV equals nRT. And we're going to do a substitution. And this is what we're going to get. dg is equal to nRT on P times dP. And we are going to integrate this. And we are going to integrate from some initial state, which we've labeled with the circle with the line through, to some final state. So you may wonder, what does this circle with the line through it mean? It means standard reference state or standard conditions. For gases, that is 1 bar pressure and 298 Kelvin. But for the moment, we are not going to insist on saying 1 bar pressure. We're just going to label it for pressure just P circle dash. All right, let's see where this is going. All right, integrate, and the integrating result is this. You may wonder, where does this natural logarithm come from? Well, that's what you get when you integrate an equation that's got the 1 on x dx form. Instead of x, we've got pressure. And since it's a definite integral, we get this logarithm with a fraction in it. All right. So, here we have the Gibbs free energy for a gas at constant temperature and just sitting there. And we can determine its Gibbs free energy if we decide to change pressures. All right, what we're now going to do is we're going to apply the Gibbs-Diom result. Essentially, we are going to divide by the number of moles, and we are going to get the chemical potential for an ideal gas, say nitrogen. And you'll notice that the chemical potential is equal to the standard state chemical potential plus RT times this logarithm with a fraction of the pressure. So that what you can see is that the chemical potential of a gas depends on its pressure. Now, the key concepts to take away. The chemical potential for an ideal gas is given by this equation. Burn it into your memory. And the standard, and that circle dash indicates a standard or reference state, usually 1 bar pressure at 298 Kelvin. All right, that brings us to the end of the lecture, and we have quite an involved quiz. So I'll just read the questions for you. Question number 1. The symbol circle dash indicates the standard state. This is the state we select as a reference against which to measure everything. For gases, we select the standard state to be when a gas is at 1 bar pressure and 298 Kelvin. Now, we have a gas whose standard state chemical potential, mu circle dash, is 0 joules per mole. Calculate, at room temperature, the chemical potential of a gas at 1 bar. Give the answer in joules per mole. Question number 2. Now we have a gas whose standard state chemical potential, mu circle dash, is 0 joules per mole. Calculate at room temperature the chemical potential of a gas at 2 bar pressure. Give the answer in joules per mole. Question 3 is the same as the first 2 questions, but this time the pressure of the gas is 0.5 bar. Give the answer in joules per mole.